Hi, today we'll be talking about not Linux ate my RAM, but RabbitMQ ate my RAM. As you can tell, this topic has been around for a while in different contexts, but today we'll be debunking the myths around RabbitMQ memory usage and specifically answering the question, why did RabbitMQ eat all my RAM? This topic was proposed by Farkey via TGIR issue 5, and we have a similar discuss in RabbitMQ discussions issue 59 started by Lyrics. So the issue that Farkey has been having is a RabbitMQ node that is using too much memory. The physical host has 61 gigs of RAM, and RabbitMQ high memory watermark is set to 24 gigs. And what Farkey is seeing is that his RabbitMQ node is using most of that memory and it's just not releasing it. So his issue is that he has a pager duty screaming at him at 2 o'clock in the morning, and we definitely want to help him to reason about it and to have a configuration that will not be using as much memory. The other issue that Farkey has been having is that when he restarts the node, it crashes on shutdown in this case, and he lost all persistent messages. That was like one incident. The other one is that he got stuck on rebuilding indexes. It's something which we will look into as well. And he keeps getting hit by out of memory. This is the Linux OM, Linux out of memory killer, which will kill any process that is using the most memory when another process wants more system memory. And even doubling up the RAM to 122 gigabytes, it didn't seem to help. The one thing which I did notice looking at some of the data that Farkey shared with me privately is that he has 500 queues. He's basically expiring both the queues and the messages in 30 days. Now, not all of his queues had clients, had consumers, and not all of his queues had a TTL. Now, do you want to guess which those queues were? Those were the queues which had the most messages. Okay, so this is a snapshot of the RabbitMQ-Overview metrics. We are looking at the new Grafana dashboard that shows a RabbitMQ-Overview. So all the metrics that you see on RabbitMQ-Overview, on the overview page, we can see here, plus a couple more. But this gives us a very good understanding of what is happening on this RabbitMQ node. So the time span is about 8-9 hours. So we're looking at 9 hours worth of metrics. And the thing which I would like to point out is that we have 50 million messages on this one node. We have a constant rate of about 3,000 incoming messages, very few outgoing. The reason why we have few outgoing messages is because out of the 500 queues, 450 queues are using, they all have producers, they all have consumers, and they consume messages as soon as they arrive. So there's no backlog in those queues. And we have 50 queues which have only producers or publishers. We publish about 3,000 messages per second across all 50. So that's roughly 60 messages per second per queue. And out of those 50 queues, they're durable. The messages are persistent, 26 kilobyte messages. And the queues have a limit. So we are limiting the number of messages that the queue can hold, and it's set to 1 million, so that in total across all 50 queues, we won't have more than 50 million messages. So what we are seeing here is that like slow ramp up, the number of messages ready to be delivered to consumers goes all the way from 0 to 50 million. This gap is interesting. We'll come back to it a little bit later, but I would like to focus on this first portion, just to understand what's happening here. So we can see the slow ramp up. We can see the disk space available going down all the way from 1.8 terabytes all the way down to 500 gigs, 600 gigs. So that's basically the messages being written to disk. Okay, so we see that the memory spikes they go from about 35 gigabytes worth of memory available all the way down to about 19, 20, but never lower than 20. While the memory is very spiky, the memory is just spiky, we can see it's like steadily over the span of, in this case, it's 4 hours. It's, using and releasing memory as we would expect all the way to down here when it reaches 50 million messages, and it's fairly stable. It's spiky, but it's stable. So this is good and interesting, but it doesn't tell us how that memory is broken down. And for that, we have another dashboard, another Grafana dashboard. It's the Erlang-Memory-Allocators dashboard. And this will give us a breakdown of the memory from an Erlang VM perspective. We need to remember that the Erlang VM is the runtime for RabbitMQ, and anything memory management related happens in the Erlang VM. So if there's any issues around memory not being released correctly, we obviously would look into RabbitMQ, but we would need to understand what is happening from an Erlang VM perspective to be able to tell whether, yes, this looks like a RabbitMQ issue where RabbitMQ maybe is not releasing memory, but also it may be an Erlang VM issue where Erlang is not releasing sufficient memory. And we will see that in a minute, because just as Linux is a bit lazy to release memory, it likes to cache it, likes to use it, Erlang can be a little bit like that as well. So we have the same timeline that we had before here. So I'm going to zoom in on this one, which is basically before the gap. And again, we'll come back to the gap. And this is what the memory breakdown looks like from an Erlang VM perspective. And the resident set size is what the operating system sees. So we can see how, from an operating perspective, the memory usage goes from about 21 gigabytes down to 5 gigabytes to begin with when memory is released. And as time goes by, less and less memory is being released, because at this point, the minimum amount of memory used is 11 gigabytes. But when we started, just when the messages only start getting published, remember this was early on where, I'm going to close this one, this was early on where when we didn't have as many messages in the system, we were releasing more memory. So the Erlang VM was basically releasing more memory back to the operating system. So from an Erlang VM perspective, the allocated used is the memory that Erlang VM allocated and is being used by something in the Erlang VM, and we'll get to that in a minute. Unused memory, it tends to be fairly low, and typically when before memory is released back to the operating system, it goes into something called the unused pool. And there's like multi-block pools. We'll get into that in a minute. But this basically means that the Erlang VM will hold on to this memory for a while longer, just in case it needs it, before it releases it back to the operating system. And we can see how it releases a little bit of memory. And then when it says, you know what, I'm definitely not going to need this based on what's happening, it releases more memory. So in this case, allocated unused, this is like a fair bit of unused memory, and then all of a sudden it says, you know what, all this memory can go, and it goes all the way down to 800 megs unused, but it released, at this point, it released like many gigabytes. The important thing to pay attention to is the relationship between the resident set size, which is what the operating system knows that the Erlang VM process is using, and the allocated used, which is what the Erlang VM has allocated to different things happening inside. There's always some memory which is unallocated and like not even allocated, unused or used. It's just basically reserved just in case it may need it, but it hasn't been given yet from an Erlang VM perspective. It's available from an operating system perspective, but the Erlang VM is not using it. So it's like somewhere in between the operating system and the Erlang VM. Okay, so moving on to the next one, allocated by allocated type. This is an interesting graph. And the reason why this is interesting is because we can see the different types of allocators. So let's talk about this for a while. The green line, let's just focus on this one for now, is called the binary allocator. And this is the allocator used for binaries that exist in the Erlang VM. So you can think of a binary as, for example, an AMQP message body. Obviously, it's more than just that, but if you think about messages being published, messages being consumed, the bulk of the binaries in an Erlang VM, in a RabbitMQ node, will be messages. Mostly AMQP messages. They can be, a different MQTT. Regardless of what they are, there will be messages. So we can see how we have 20 gigabytes at the peaks being used for messages and then released when it's no longer needed. So we can see that the bulk of the memory in the system is used by binaries, which in our case, it's messages. And actually, in most RabbitMQ nodes, the binary allocator is showing how much messages, how many messages there are in memory. So that was the one. The other very interesting one is the ETS allocator. And we can see how this one keeps increasing all the way from a few hundred megabytes all the way to 7.9, almost 8 gigabytes. So ETS stands for Erlang Term Storage. Those are data structures, in-memory data structures, very efficient, which can get queried by different processes. So they are shared, or they can be shared. And in this case, the bulk of this memory is used by something called the queue indexes. So we have like all those messages in the queues. For every message that we have in a queue, we have an index, a message index, which holds some metadata for that message. In our case, because we have so many messages, we have 50 million messages, there will be a lot of memory used to keep track of where the message is. So I think now, with this information, it's easy to see as to why the memory used goes up and up and up. It just goes up because not enough can be released, since a lot of this memory keeps growing in the ETS allocator. Do we have anything else interesting? I think the other interesting one is the eheap one, which I would like to cover because this does use some amount of memory. So the eheap allocator, these are I think the three worth remembering. The binary one, which is for messages. The ETS one is for basically in-memory data structures that a RabbitMQ node uses for metrics. And in this case, in most cases, to know the position of messages in the queue. And the third one is the eheap one, which is the allocator used for process memory. So if you think about a process that has a stack and it has a heap, and it's the type of memory that is being used for doing all the work, right? If you have, for example, a map and you have to iterate over it, any sort of work that the process needs to do, or any sort of state that the process needs to hold, it will use some memory. And let's take a look at the binary allocator now. So this whole section. Actually, you know what I'm going to do? I'm going to collapse all of these, and I'm only going to open specific ones so that we don't get distracted. So looking at the binary allocator, multi-blocks. Okay, I think this is a good point to introduce multi-blocks and single blocks. Okay, so memory in an Erlang system comes into, actually, let me think how to put this. Okay, let's say that you have items that you need to put somewhere, right? A book, a bottle, a keyboard, whatever it is. And let's imagine that those items are the equivalent of the memory blocks, the actual memory blocks that need storing somewhere. In an Erlang VM system, you have something called carriers. And the carriers are like boxes into which you can put those items. And the Erlang VM, or the Erlang allocators in this case, when you get allocated something to put basically stuff into, in this case, things into, you get allocated carriers. So carrier is nothing more than just a box. The multi-block carriers are boxes in which you put more things, more than one thing. And that typically happens if you have like a small item. So let's say that you have 1 kilobyte worth of data to store into memory. You will put it into a multi-block carrier because you can have different shapes and sizes of items. A single block carrier is the type of box where you can only put one item. And the single block size, it will vary, so it will not always have the same size. And it will try to approximate it based on what you're trying to fit in. The multi-block used, so this is I think where the bulk of the memory is, and that it gets used and released, and those carriers get released. I don't see anything. I mean, they do spike slightly, and there's like a constant use of the multi-block unused, but they don't grow. The ETS one, however, it goes all the way to 2 gigs. So this has a very different profile, usage profile from a perspective on allocator. So whatever's happening in ETS, and we can see that here, it's starting to go down, and we're starting to release it. Whatever's happening in ETS, that's what is contributing to our unused memory up here growing. It stabilizes, we can see that it grows for a while, and then from here onwards, from 5 p.m. onwards, it kind of goes stable. And I think that matches what we're seeing here. Yeah, look at that, 5 p.m. and at 5 p.m. this one starts going down. However, this one starts going up. So they kind of balance one another out, I think. So we have, let's see, 2.6 all the way down to 2.2, so 400 meg, but we have like another, that's actually too little. So we're still missing single block unused. No, that's not even an issue. Multi-block, there you go. So between these two, that explains it. Between multi-block unused and multi-block pool unused, we are seeing how the unused memory will remain more or less stable. I mean, we do have like these spikes and drops, and eventually it will get released. But we have a lot, in this case, a couple of gigs. No, it's not a lot. We have a couple of gigs of unused memory. We have a few gigs of unused memory in ETS alloc. So from a memory breakdown perspective, there's no unknowns, there's no surprises in the system. We can reason where the memory is being used, how it's being used. We can look at binaries, which are the messages that are flowing through the different processes inside of the Erlang VM. We have the ETS, the queue index. Most of it is used by all the queue indices because we have 50 of them. And actually it's 500, but the others, they have no messages. So 450 of them are okay. So between the 50 queues with lots of messages for the queue indices, some metrics, they will only use some meg, so it's not a lot. That's where ETS is going. And the other one, the eheap one, which is used for processes, again, it's not a lot, so there's no surprises here. I suppose the only thing which corresponds to these spikes are these spikes, which is the binaries. So messages being evicted from memory. Okay, let's talk about the gap. When I mean the gap, when I say the gap, I mean the time in between 1:25 and 2:21 roughly. So we have roughly an hour of no metrics. Why is this? So the thing which I noticed is that when the RabbitMQ app is stopped and started, all the queues, the queue indices need to be rebuilt. So all the messages that are stored on disk, we need to read them all to rebuild the queue index, and then something else happens. I would very much like to understand what happens, because I haven't looked close enough in the code to get to that part. But the observation is that when the node gets restarted, a lot of memory is used, and I'll zoom in on this, a lot of memory is being used by something called the worker pool. So in this case, the worker pool process is using 56 gigs worth of memory. And that is a lot. That is a lot of memory to be used by a single process. The worker pool is a manager of workers, and we are using worker pool in RabbitMQ node to perform all sorts of tasks. In this case, we are using different workers to rebuild the indexes and to rebuild the state, the view of the queues when a node boots. Now, the worker pool, it must be constructing a very, very large data structure. It's 56 gigs large, it's crazy large, and then it has to go over it as a single process and give work to the workers in the pool. And in this case, that happens when a node restarts. So when we have durable queues, deep durable queues with a very big backlog, the worker pool on node startup, it's using a lot of memory to rebuild those queues. And I say that, but going through this, let me just jump. So we can see that right here, let's take a look at this. So this is like regular, so this is a view of the system memory. And we can see the spikes and the drops from, this is like from an OS perspective. We can see that most memory is cached. So that's like the blue one. Some is used when node is running normally. And then the RabbitMQ app is stopped. The Erlang VM is still running, but the RabbitMQ app is stopped, which stops all the queues, the message stores, the vhosts, everything. And then it gets restarted. So when the app gets restarted, we have about 15 minutes here, 15 minutes, where the queue indices get rebuilt. And that will use some memory. So we've seen like that's the ETS one. And then the next thing that happens is really interesting. Then we have a massive spike of memory all the way to 80 gigs, which eventually drops. And then we have a steady use of 60 gigabytes. Most of it, we've seen that it's used by the worker pool to do something. And looking at the code, I couldn't figure out what exactly it's doing. I can see the function call, but that's not very helpful. In the case worker pool, where is the state? No, initial call, it's not that one. I'm trying to remember where I've seen that worker pool. Gen server, that's it. So the current function, most of the time, it's spent in gen server to drain. And we can see that the other workers are, so this is the worker pool manager. The other workers are gen server 2 process next message. So I'm assuming they're iterating through the messages one by one. However, most of the memory is used by the worker pool. So when a node gets restarted, we can see also, and that coincides with a very heavy disk reads. So when a node gets restarted and these queue indices have to be rebuilt, the disks are read a lot. So the disks, in this case, it's reading at 410 megabytes per second. And it maxes out at 965. And that is like 10 gigabit. So this is a disk which is reading for about 15 minutes at 10 gigabit. So 10 Gbps. That is very heavy read. And that coincides with very high memory usage. Everything drops. The connections get reestablished, and then the publishing resumes. So we don't have the answer to this yet, but the thing which we are noticing, and I think this is something that Farkey noticed as well in this case, is that the queue indices, the node startup seems to be stuck. It's not stuck, so things are happening. We can see that things are happening. but they require a lot of memory. They do a lot of disk reads, and by the way, you may not see this. So dstat, iostat, whatever you have running. In this case, we're using net data to see what the disks are actually doing, and if the disks can't read at this rate, obviously it will take longer, right, to read all the messages on disk. I was wondering, the next thing is, what happens if we use lazy queues? So we know that lazy queues have a better memory profile because they keep as little of the messages in memory as possible. They just go straight to disk. So you'll have a higher disk I/O in that case, but a lower memory usage. So that seemed like a good thing to try next. Okay, so this is the view, similar workload. We go from 0 messages to 50 million, but in this case we're using 50 lazy queues. We're not using 50 durable queues. And right off the bat, we can see how the memory usage is not as spiky. It's almost like a straight line. And if we compare it to what we had here, you can see how spiky, and this was actually, this was before the gap. We can see how spiky the memory usage is here. So compare this with this, flat as a pancake, right? Really nice memory usage. The messages ready to be delivered to consumers, so they go up, and this space available, this like goes nicely down, and so we have the same workload, but the memory usage is much nicer. Let's take a look from a Erlang memory allocators perspective, what that looks like. And we can see a very similar trend there, in that the resident set size keeps going up, the allocated used, even though there's like a little bit of difference. So in this case, we have about a gig, right? There's always 900 megabytes to a gig of unused memory, but it's steady, very, very steady. Something happens here. So the thing that happens here is that the limit gets applied. So at this point, we have filled the messages, and we are starting to drop messages from the head. That's like the default strategy when the max queue length is reached. This is configurable, by the way. You can also reject new messages. You can reject or you can drop incoming messages, but by default, the oldest message gets dropped to make room for the new messages. And when that happens here, when that starts getting applied, we can see that the memory jumps from 9 gigs to 10 gigs. So there's like about a gigabyte extra. Now the memory keeps increasing, and the next chart is showing us why that happens. So even though the eheap and the binary, the binary specifically, look how little binaries we have in the system, right? Up to 500 megs. These are like the messages. So very few binaries. The thing which keeps increasing is the ETS, and that's the queue indices. So we still have to keep track of all those messages, the position in the queue, and so on and so forth. And that goes up and up and up all the way to 8 gigs. So the bulk of the memory used, which in this case is 10 gigs, is actually ETS, right? So like 80%, 80+% is ETS. And the eheap, that's basically the processes. Again, they need less memory. So we're seeing that all the processes across the entire node, they need up to a gig. While before, I think when we looked here, where was it? Allocated by type. Let's take a look at eheap. So we can see the spikes, right? The processes using up to, in this case, we even have like an outlier at 2 gigs. This one here, 1.96 gigabytes. And we have a very different picture here where they're using, up to a gigabyte. So this is a much nicer memory profile. And from the perspective of memory usage, this is definitely the more memory-friendly queue type in this case, especially since messages are going to disk anyways. So if I had to choose between this and this, I would definitely choose this. The total memory is lower, so you can see that the spikes here are 20 gigs. And also like the memory profile is much nicer. So actually, in your case, Fark, you don't even need actually 60 gigs. You can do with possibly 30, so half of that, maybe even 20. And actually what I would recommend is actually even having less memory if you are more aggressive in how you evict messages or how you limit the messages that are in a queue. That's what I would do. I would constrain the queues to have no more than, maybe even 1 million is too much. Maybe 100,000, maybe. I don't know if you can do that. So that's what I would recommend. Okay, now, unfortunately, and I'm not showing this here, but unfortunately you will have the same problem with the message recovery, right? So whether it's a lazy queue or whether it's a durable queue, when it has to recover all the messages from disk and it has to basically rebuild the queue index, it's that worker pool that will use a lot of memory if you have a lot of messages. So the quick fix is to not have a lot of messages, right? If you can do that, when I say not a lot, a few million is fine. But if you have a couple of tens of millions of messages, you should be prepared to need a lot of memory. So yeah, use lazy queues. They're better than durable queues in this case, but you will still have like the slow startup, and you will require a lot of memory to rebuild the queue index and then read the messages. We will get back to you on that because that's something funky which I would like to understand more. Right, so I would like to switch gears now and talk about a different use case. Specifically, lazy queues consume too much memory and hitting memory alarms. So lyrics, this is a discussion, lyrics Grégoire Pinon. So he mentioned about his issue. He has a PHP consumer. It mentions further down for recreating it. And his problem is that his node is using a lot of memory, like 1.1 gigabytes. Now, I recreated Grégoire's or Lyrics' environment, and we can see here we have 100 messages, up to 100 messages. The memory usage is actually fairly low, and it stays steady. So this is, again, the memory allocators. Let's just focus on the resident set size. It goes up to 300 megs. So using your workload lyrics, and actually even like I added more messages per second. So in my case, I'm publishing 10 messages per second, and they're all 1 megabyte messages. You're only publishing 1 message per second. And I've been running that for, in this case, I think it's like 2 days. So yeah, it's 2 days, day and a half, 2 days. And we can see that the memory usage is fairly stable, fairly flat. So I'm not seeing your problem. It's spiky here, and that'll be something worth looking into for sure. Like, why is it this spiky? But when I say spiky, it's the resident set size. The allocated one is fairly stable. Also, the allocated unused is fairly stable. By the way, this is before and after the gap, but the time span is much larger. So if we zoom in a little bit, you'll see that this gap here is also 137. I can't quite remember what happened there, but still, like, the rebuilding takes just as long. Maybe that's another gap. Yeah, definitely that's another gap. The point being that the usage, I'm not able to recreate your problem. So I think that is down to your environment. And this is net data. This is the same one. So we can see the memory usage here. And I think the thing which I wanted to point out is disk. We are writing and reading 10 megabytes per second. Megabytes per second. And the RAM, again, this is, we're looking at a day and a half. It's fairly flat, right? So no problem. There was a follow-up to the first episode. The first episode, for those of you that do not remember, let's take a look at the pull requests. This is the one that was just closed. It was how to upgrade from RabbitMQ-37 to 3.8. So that's already out there. And that was like the first episode. And one of the questions was how to upgrade from 3.6 to 3.7? Is it supported? And we were able to perform an in-place upgrade. I literally did exactly the same. I did exactly the same process as I did from 3.7 to 3.8. I just added a new image, and we can see the instructions here. The conclusion is that going from 3.6.16 to 3.8.2 took 3 minutes and 47 seconds. And most of it was the GCP deleting the VM. It apparently it's an operation that takes about 2 minutes. And then another one was booting the VM. So that was like a fairly straightforward upgrade. Now, we do not support 1 by 1. So from going from 3.6 to 3.8, everything has to be stopped. The last stop node has to be started first. But an in-place upgrade from 3.6 to 3.8 is possible if all the nodes in the cluster are stopped. We can't have mixed mode. It's possible 3.7 to 3.8, but it's not possible 3.6 to 3.8. As long as everything is stopped and then node is started, it'll be fine, as I demonstrated here. So that was like the first thing. The next thing, part of this thread, the question was around startup node boot when there are many vhosts. So as this reply captures, every vhost has its own persistent and transient message store since RabbitMQ-370. So this has been around for a bunch of years now, I think 3 years, at least 3 years. And every vhost is expected to add about 1.5 seconds to node boot. So if there are 1,600 vhosts, as was the case of this person, and this is like, it can be an upgrade, it can be just like a regular stop and start, it doesn't really matter what it is expected for node boot to take about 40 minutes, just for the vhosts alone. I mean, as we've seen in this episode, if some queue indices have to be rebuilt, if some messages have to be read, whether it's a quorum queue, in this case, it is like a 3.8, it will take longer. So in this user's case, taking 1 hour, about 1 hour for a node to boot was normal because there were so many vhosts. So another pro tip, don't have that many vhosts. I mean, if you have more than 100 vhosts, maybe that's enough, and maybe you should need a different cluster or a different node, because having too many vhosts on a single node, it will impact the startup. Lastly, this is again a comment regarding the last episode. Marques Johansson, he's from a good friend from Upbound and Crossplane. He was saying that, hey, didn't you take inspiration from TBS as well? TBS is also a series of episodes similar to TGIK that I was mentioning as the original inspiration for TGI RabbitMQ. Marques noticed that, well, TBS is very similar to TGIR, and actually I was waiting for him to notice that. It was like a little inside joke to see if he will pick it up. He will pick up on that. He did, and TGI RabbitMQ, this series of episodes is inspired by TBS as well. I'm a big fan of what the Crossplane folks are doing, Marques and Daniel and Jared, a great bunch of folks. And yeah, I mean, this show is also inspired partly by what they do, but still mostly by TGI Kubernetes. And with that, thank you very much for watching. See you in a month's time.